Pick up something near you, a snack box, a book, or a passport. Under the barcode, on the back cover, or at the bottom of the passport's identity page, you will find a long row of characters. We usually assume it is nothing more than a product code or an identification number. But inside many of these rows, one character is acting like a secret inspector. It does not tell you what the object is. Instead, it checks the rest of the row. If a reader misreads one digit, the check can expose the mistake immediately. It can also catch many cases where two digits are typed in the wrong order. How can one character do that without querying a database? Today, we are taking apart the numbers that keep checking themselves. Start with the barcode on a product package. There are many digits under those bars, but the most interesting one is the final digit. That last digit does not carry product identity on its own. It is called the check digit. The check digit is calculated from all the data digits before it. The method takes each digit, multiplies it by an alternating weight, and adds the results together. Then it asks one simple question. How much must be added to reach the next multiple of 10? That missing amount becomes the check digit. When a scanner reads the barcode, it reads the full row and calculates the check digit again from the data digits. If the value it calculates matches the final digit, it read. The row is internally consistent. The scanner accepts it and gives the familiar beep. If the two values do not match, at least one digit was read incorrectly. The scanner rejects the row and asks for another scan. In other words, the barcode carries its own answer key. The scanner can compare it every single time. Now turn to the back of a book and look for its ISBN. Like a barcode, an ISBN 10 code places a check character at the end. But ISBN 10 has a stranger twist, and it explains why some book codes end with a letter. To calculate the check value, the data digits are multiplied by descending weights. The products are added, and the result is evaluated using division by 11. That process can produce a check value from 0 all the way through 10. But a single decimal digit can only represent 0 through 9. There is no one-character decimal digit for the value 10, so the designers borrowed a Roman numeral, the letter X, which represents 10. That means an ISBN 10 code ending in X is not a printing mistake. It is telling you that the calculated check value for that book is 10. Once you know what X means, that one character reveals the hidden arithmetic behind the whole row. Finally, move to something with higher stakes, a passport. At the bottom of the identity page are two long lines of letters, digits, and angle bracket-like filler characters. Together, they form the machine-readable zone, or MRZ. Those lines pack in a great deal of information, including the holder's name, passport number, date of birth, and expiry date. At border control, a machine has to read those fields quickly and accurately. So the passport does not rely on just one check digit. It places check digits in several locations. The passport number has its own check digit. The date of birth has another. The expiry date has another. Each field can therefore be checked on its own. Then one final composite check combines key fields and their check digits in one more calculation. It is a second layer watching over the first layer. If a character is read incorrectly, the recalculated field value can stop matching. The composite check provides another chance to expose the inconsistency. That is how information used across borders can carry several layers of local error checking, without needing an internet connection for the arithmetic itself. Now look back at all three systems. A barcode uses a check digit calculated from the other digits. ISBN 10 does the same thing, and sometimes has to borrow the letter X to represent the value 10. A passport uses several field checks plus a composite check, because the cost of a bad read is much higher. All three rely on the same idea: deliberately add something that seems unnecessary. That extra character does not add a new name, date, or identity. Its job is to confirm that the rest of the information still fits together. The result is a system that can notice many typing or reading errors as soon as they happen, without asking anyone else for the answer. And the idea does not stop with these three examples. Bank account numbers and QR codes use related forms of redundancy to detect and sometimes even correct mistakes. The next time you see a long row of numbers on an everyday object, take another look. One character in that row may be working quietly as a secret inspector, checking everything around it. That is the extraordinary idea hiding inside an ordinary line of numbers.